State the Doppler effect in words. Of course, we're going to skip that. Let's do 6.2. Use the information given to calculate the speed of sound in air. Mark allocation 5 marks. So let's go ahead and take a look. A stationary listener records the frequency of the sound emitted by the siren of a police car. When the car, which is traveling at a constant velocity, so we have the velocity of the source right away. So Vs is 26 meters per second. Approaches the listener, the recorded frequency is 615 hertz. So the velocity, not the velocity, but the frequency that the listener records, the frequency observed, is 615 hertz. This is when the car it is moving towards. The car passes the listener at t is equals to 1. At time t is equals to 1. Okay, right. And then moves away from the listener. The recorded frequency is now 526 hertz. So this is towards 615. And then when it is moving away, we have Fs, not Fs, but Fl, which is 526 hertz. Use the information given to calculate the speed of sound in air. Okay, not quite sure how we're going to do this one, but take a look at this. Let's stick to the basics. Let's start with this case where the kite is moving towards. So we're going to have FL being equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. This is the formula as it is before we do any modification. You get a mark for the formula. Now we can modify it. FL is equals to V is the listener stationary, a stationary listener. So the listener is stationary. So we just have V divided by V plus or minus Vs. So we have V, speed of sound in air, of which we're trying to calculate. And then Vs, that of the source. The source is moving towards, right? So we're going to have minus 26 multiplied by the observed, multiplied by Fs. We know FL when the listener, when the sound source is moving towards, it is 615 hertz. So we're going to have that there. So there we go. We have these. We can't proceed anymore because we have two unknown variables. Let's take a look at the case where it is moving away. When it is moving away, the observed frequency, okay, the observed frequency is 526 hertz. And then we have V divided by V. Now that it is moving away, you're going to have plus 26 multiplied by Fs. Fs is all the same because that is the emitted frequency. So we have these two equations. We have this equation 1 and this equation 2. And what we need to do is to solve simultaneously. That's what we need to do. So how can we possibly do that? Well, we have two unknown variables. So it's either we make Fs the subject of the formula in equation 1 and substitute in F2, or we can, what else can you do? We can make V subject of the formula in equation 1 and substitute in equation 2. Whatever we decide to do, it's all going to work out. So let's take a look and see which one is the easier case here. Can we easily make Fs subject of the formula in equation 1? I think so. Let's take a look at what we can do. So with equation 1, we're going to say 615 everything divided by V divided by V minus 26. This is equals to Fs. We're just dividing everything by the coefficient of Fs. But we can switch that division into a multiplication, right? If you are dividing by A divided by B is the same as multiplying by B over A. So we can apply that idea to get over that hurdle. So let's go ahead and do that. 615 multiplied by V minus 26 divided by V. We can write it like this instead. And this is Fs. Okay. Let's further simplify it. 615 multiplied by V is 615V. And then we have 615 multiplied by minus 26. That is minus 15,990, everything divided by V, right? This is Fs. So let's substitute these Fs into our equation 2. Okay, so if we do that, can we take this to the left hand side first? Can we take that to the left hand side first? Okay, let's take that to the left hand side first. If we take that to the left hand side first, we're gonna have 526 multiplied by V plus 26 divided by V. We are applying what we applied on the first equation. Obviously, let's multiply out before we substitute Fs. So 526 multiplied by V is 526V. And then plus 26 multiplied by 526. That is, oh, okay, here we have V, here we have V. And then plus 13,676, everything divided by V. This is equals to Fs. Now, in place of Fs, we're gonna then substitute these which we have here, right? So in place of Fs, we're gonna substitute 615V minus 15,990, everything divided by V. Think we're getting somewhere. Because we are dividing on the left side by V and dividing on the right side by V, we can just drop V, because the numerators must be equals to each other for those two things to be equals to each other. So right, we're just gonna have 526V plus 13,676 being equals to 615V minus 15,990. I think it's quite simplified now. Let's take these to the left hand side. So 526 minus 615, that is minus 89V being equals to minus 15,990 minus 13,676. That is equals to minus 29,666. So V is equals to, we divide that by minus 89. Let's take a look. I'm getting 333.33 meters per second. That is not a bad value of the speed of sound in air. It is not alarming. If we were getting something like 1,000, we would be very surprised. Or if we're getting something like 200, we would be very surprised. So the math that I applied here, I mean, it is not the only way you can solve this question, right? The concept is the same, but then the math can be completely different depending on which variable you are making the subject of the formula, so on and so on. But essentially, at the end of the day, we should get the same answer. That is 6.2. 6.3, calculate the wavelength of the sound emitted by the police siren. Okay, we want the wavelength of the sound emitted by the police siren. That is out of 4 marks. So the siren emits Fs. This is what the siren emits. And then V is 333.33 meters per second. So we have V. We are looking for the wavelength. So V is 333.33 meters per second. Fs, we can calculate it, but at this point, we don't have it. So how are we going to calculate Fs? We have this equation here. So we're going to use that equation to calculate Fs. So Fs is equals to 526 multiplied by V is 333.33 plus 26 divided by 333.33. So let me put that in my calculator. 526 multiplied by 333.33 plus 26, everything divided by 333.33. Right. And then when I put that in my calculator, I get 567.0284 hertz. I can actually prove if this is correct, but I don't think it's necessary. I'm quite sure this is correct. Okay, so we have Fs. So now we just need the wavelength. The frequency is equals to the velocity divided by the wavelength. So the wavelength is the velocity divided by the frequency. So let's substitute here. 333.33 3.33 divided by 567.0284. Okay, 333.33 divided by 567.0284. This is 0.59 meters. So there we go. We have the frequency. Now 6.4. Sketch the graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then moved away from the listener. Labeled time t1 on the graph. No values needed to be indicated on the frequency axis. Okay, so let's take a look. First of all, we need the frequency axis. So there we have it, and then we have the time axis. So let's take, what am I doing? Right, so this is the time in seconds, and then this is the frequency in hertz. Have you heard? We don't need to include any values. Okay, so initially, is it moving away? It approaches initially, right? And then after that it passes and moves away. So when it is approaching, we have a higher frequency. So somewhere here, this is our frequency when we are approaching. And then something happens at T1, right? Something happens at T1. At T1, it passes the listener and it's now moving away. So we are expecting something like this. The frequency is going to decrease. The frequency is going to decrease. I was supposed to indicate something. Sketch the graph as it moves towards. Okay, I don't know. It doesn't say we must indicate which one is towards. But here, this is towards. As it is moving towards. This is away. And then somewhere in the middle here, we have the emitted. There we go.